Okay, so in this video, we're going to do another example of strong induction, and this will introduce you as well to um, some new mathematics potentially if you've never seen recursively defined sequences. So here's the example. So consider the sequence, which is recursively defined by the following. So first member of the sequence is 1. Second member of the sequence is 3, but then the recursive part is that the nth member of the sequence is given by taking 2 times the n minus 1th member and then subtracting the n minus 2th member. And this is true for any n bigger than or equal to 3. Here, it's already assumed that n is a natural number in this formulation. So just to make sure you understand what this definition is, well, I haven't even told you what we're going to prove yet, but just to make sure you understand what we're dealing with here, let's start to just work out the first couple of elements of this sequence. So I'll start off by listing on the side here. And then, of course, the first one we don't have to work anything out. It's just told to us that it's 1, and the second one is 3. So you always need these like seeds, if you will, to start off any recursion. So the first 2 just need to be given to you. And if you change the first 2, it'll change everything else, even if you don't change the recursive formula. So now if I want to find A3, then the recursive formula says, okay, n is equal to 3. So now this is like 2 times A2 minus A1, right? Because I'm plugging in n equals 3 into this formula. So on the right-hand side, I get A sub 3 minus 1, that's A sub 2. 2 times that minus A sub 3 minus 2, that's A sub 1, right? Okay, but now I just plug in what those things are. So that's like 2 times 3 minus 1, so that's 5. Perfect. A sub 3 is equal to 5. Now what's A sub 4, right? We just keep going. So A sub 4 is 2 times A sub 3 minus A sub 2. All right, well, now I know what A sub 3 is. So that's like 2 times 5 minus 3. And so we get 7. Okay, continuing. Then the way this recursive formula always works, you're always like just in time for the next thing that you need, right? So now it's like 2 times A sub 4. Well, we just got A sub 4, right? So we're just in time with what we need there. And so that's like 2 times 7 minus 5. Well, that's 9, right? And now we start to see this pattern playing out that we can't help but wonder if it's going to persist. Let's just do one more. 2 times 9 minus 7. So that's 11. Okay, but now we seem to be getting the odd numbers, right? We get this recursive formula that's given in a slightly more complicated way than it seems to need to be because we're just getting odd numbers. So again, we could continue this, but we'd have to stop at some point. So now we want to prove that actually A sub n can be given by a non-recursive formula, just a closed form formula that it's just equal to an odd number expressed by 2n minus 1. And we've seen that 2n minus 1 gives us odd numbers, right? Okay, so let's see, right? Let's see what happens. So how are we going to prove this? Well, you'll see it's going to involve some strong induction. And so let's do a proof sketch, right? So proof sketch. So here we're just going to play around. And we're just going to play around with the inductive case. So let n be a natural number. Now we'll be more explicit about that and assume for all natural numbers, this is the strong induction assumption, right? So for all k less than or equal to n, that we've already shown this formula to be true. And then consider Okay, so now we consider a sub n plus 1, which is 2 sub a 2a sub n minus a sub n minus 1. That's the next one after n, right? So I had to increase everything by 1. Remember, the formula for a sub n is given up here. If I plug in a sub n plus 1 instead, then this next one is n plus 1 minus 1, so that's a sub n. And the last one is n plus 1 minus 2, that's n minus 1, right? So that's where this formula comes from. But now both the a sub n and the a sub n minus 1 fall into the range of the strong inductive hypothesis. So I can just replace it saying it's that one is in the range of the strong inductive hypothesis, minus this one is also in the range, right? Because we're assuming that the inductive hypothesis holds for anything, any natural number k less than or equal to n. Well, n is less than or equal to n, and n minus 1 is less than or equal to n. So we get this, and now we just have to show that this works out. So what do we get? We get 4n minus 2 minus 2n minus 2 minus 1. So that's minus 3. So that's going to be, let's just write it out. 4n minus 2 minus 2n plus 3. And that's, of course, the same thing as 2n plus 1. And notice that 2n plus 1 can be written as 2 times n plus 1 minus 1. And that's exactly what we're supposed to show, right? Since n plus 1 is what is the subscript of the a n plus 1 is what's supposed to show up in this formula. And so we are good to go. Okay, now that was a proof sketch. So now we have to go back. Now that we understand how this is going to work, we just have to go back and do the sort of writing assignment, if you will, of writing the proof carefully. Okay, so now we'll write the proof. And here we're just going to tell the reader that we will proceed by strong induction. Okay, so what's the base case? We didn't even check the base case in the sketch. Well, we just need to check actually the two, there's two base cases because we need to check both of the seeds, the starting seeds, right? So A1 is equal to 1, and we just need to check that that is 2 times 1 minus 1, and it is, so that's fine. And then A2, which is given to us as 3, and that's 2 times 2 minus 1, and it is. So we're good. And now we do the inductive case. Okay, so now, again, assume for all natural, let me move myself up here. Now we assume for all natural numbers, k less than or equal to n, that a sub k is equal to 2k minus 1. Okay, that's the strong inductive hypothesis. And then we're going to take them through this calculation, right? So a sub n plus 1, which is the next thing in the inductive ladder here. Well, by the recursive formula, this is what it's equal to. That is just given to us by definition. That is what a sub n plus 1 is. Okay, now we get to use the inductive hypothesis. So maybe we should say then by the inductive hypothesis, just to, I mean, we could assume that they realized that, but it's maybe helpful to say. And so we can then kind of tidy this up a little bit for them. That's like 4n minus 2 minus 2m plus 3. They can fill in a little more details there if they like. So we get 2m plus 1. And we just point out to them that that's the same thing as 2 times m plus 1 minus 1. So we are good. So now we say by the principle of strong induction, we see that a sub n is equal to 2n minus 1. Perfect, and that's the end of the proof. So there is another example of using strong induction, and we'll see one or more two examples, going forward.